तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the two previous lectures, I introduced two modes of data transfer, that is essentially with regard to the CPU IO interaction. Okay. The first one in which the CPU takes the initiative, that is called the programmed IO, that is the CPU runs a program and effects a data transfer, and that is entirely up to the CPU, which means as per the given program. Okay. The sequence in which the different devices will have to be checked for its readiness, for their readiness, etc., will all be programmed. One can, by changing the program, one can alter the sequence and so on. Fine. The problem with that particular thing was, because it is at the CPU's initiative, as and when the device is ready, the CPU may not be aware of it, and hence it may not scan that particular, that is check the status of the device and know that it is ready, and so there is a possibility that the data could be lost. Okay? That is what it is. So, we moved on to the second one, in which what we said was checking whether the device is ready is not left to the CPU, but as soon as the device is ready, it will indicate to the CPU that it is ready by generating what is known as an interrupt signal. So, this is in fact an interrupt driven input output scheme, meaning the CPU does the data transfer as in the previous case, okay, but checking whether the device is ready is not left to the CPU. The device itself, when it is ready, informs, and then we in fact in the previous, specifically in the previous lecture, we were looking into the details of how this particular thing works. Essentially, it is something like switching from a main program or a main routine to a subroutine. Okay. A CPU executes a main program and then there is a call to a subroutine. Okay. So, it jumps to subroutine. Similarly, in this particular case also, the CPU is involved in some processing. Okay. We can call it as a main processing or a main program, and then subsequently when the device interrupts, the CPU's attention is turned away from the main program to the service program meant for that particular device. So, here also we talk about a switch from main program to the device interrupt service program, or generally called an interrupt service routine. Okay. So, in that particular process there is some delay. Why? Because after the device has been serviced, the CPU must switch back to the main program, is it not? The CPU doing something, the device when it is ready is going to indicate and interrupt the processor. The processor activity is interrupted, then it is going to attend to the interrupt service for the particular device whichever is interrupting. At the end of that interrupt service, the processor must continue with the whatever it was doing earlier. That is, it is something like switching back from the subroutine to the main routine. So, the necessary information for that must have been stored earlier prior to switching over, okay, to the other context. So, that is going to cause some delay, that is number one. Number two is the CPU is running at its own speed and device is going at its own speed. Okay. There is no synchronization between these two. These two are two independent things, except when there is some transfer. Okay. Fine. Even then synchronization will be with reference to the interface and not with the device as such. Fine. Now, so we say that the device will interrupt the processor, and that interrupt is generally characterized as asynchronous, okay, input. Asynchronous because it is not synchronized with the processor's main clock. Okay. So, interrupt is in fact an asynchronous input to the processor. And when can the CPU be interrupted? We saw this also in the previous lecture. We saw that the CPU should complete the current instruction cycle and then only take up, okay, that is prepare for the context switch, which means there is some more delay, that is in the current instruction cycle itself there is some delay, is it not, because it has to be completed. Okay. So, we saw that. So, there is some delay in this CPU turning its attention away from the main thing to the specific device. Now, what if the device happens to be very fast? That is, it cannot wait for the delay, mainly because it is too fast and it keeps generating the data very fast. Then there is a possibility that the data may be lost. Okay. In which case, what is to be done? What is to be done? The CPU is involved in the data transfer, and the CPU must continue with whatever it was doing before the interrupt, after the interrupt service. So, we have no other choice really, the instruction cycle must be completed. So, this is the minimum thing. Okay. So, in which case we say that if the device is too fast that the CPU's delay from switching from the main to the interrupt cannot be tolerated, if that is so, then the only other way is the CPU just cannot be involved in that is what we mean. In other words, the CPU must be cut off from the main activity, mainly because this, what we say is the CPU is too slow for this particular device, that is what it means. The CPU cannot handle the situation, CPU is incapable of doing it, that is what it means. In which case the device when it indicates to the CPU, and of course, this is meaningful for the fast device. Now, there are two things. We talk about a fast device, it is like this. Generally, a fast device will be generating a bulk of data, mainly because it is too fast. It is meaningful to keep generating the data at a very fast rate. It is possible that to initiate, that is initial period when we first check whether the device is ready, etc., that may take a long time. Okay, we are not bothered about that. Once the device is ready, it is something like a machine gun, okay, data keeps coming, but to load the machine gun and then to aim, all these things will take the same amount of time, whether it is an ordinary gun or a machine gun, is it not. So, the same situation here too. Now, when the device is very fast and is generating a bulk of data, it is meaningful to allow the device to put the data say in the memory directly. So, we are coming directly means the CPU is not involved, something else must come. Why? Because the CPU is always considered the master of the bus, is it not? If the CPU is cut off, something else must mastermind the whole process. So, we are moving on to the third one, in which CPU is replaced by some let us call it as a controller, we will talk about it, but the precise method or the mode of transfer is briefly called DMA, as the name suggests. It is direct memory access, that is what it is. DMA stands for direct memory access. That is, what we say is the IO device is going to access the memory directly, the CPU is not involved in it, it is going to access it directly and then store the data. Now, obviously, what we are assuming is the memory is fast enough to respond to the device request. Okay, that is all right. Memory is anyway is going to work at electronic speed, fine, good. Now, we said CPU is not involved, then what else is, because there must be something which is master of the bus, right. So, for this purpose there is a specific chip, okay, or we may say a circuit if you want, which is called a DMA controller. That is, this DMA controller is going to take the place of CPU, right. Earlier CPU was involved, no, now the CPU is cut off from the bus. Now instead DMA controller will take over and it is going to play the same role as CPU, but CPU is a very general purpose processor, whereas a DMA controller is a special purpose processor. Okay. This is specifically for the special purpose, and what is that purpose? Essentially it is to see that the data that is generated by the fast device is routed to the memory, okay, just for that purpose. And remember I said we generally deal with bulk data, generally we talk about as a block of data, okay. Say a block of data of say 1K size, 2K or 512, even less if it comes to, but specific block. Okay. So, what we say is the CPU is cut off from the bus and a DMA controller will take over, right, and that particular one, okay, is going to sit on this bus necessarily, right. The DMA controller, now you can see I have to introduce the controller here. What is the best way? Just seeing, suppose I can make use of the same set of signal lines that are there in the bus. Okay. All right, I think I will draw another sketch possibly, okay, because some of this, the address, what else, address, control, data, all these lines can be used. Why? Because the bus is not in use by the CPU as such. Okay. So, this part will be generally what is known as maybe not this part, maybe this part. Okay. The CPU is cut off, that is the essential thing. The CPU will be cut off and then the bus is still available. Now, assuming the bus can accept this data transfer, okay, can respond to the speed at which the data is coming, okay, can cater for this particular transfer, then it can be used. Otherwise, of course, a separate bus lines can be used, but generally it is not so. The DMA controller, you can say, is going to sort of replace the CPU and sit on the bus, and so okay, I just put it as DMA controller, okay, is introduced. Now, any fast device is going to send its request to DMA controller and the DMA controller will indicate to the CPU, okay, that there is a device which is ready. Specifically, we can say this is also part of the bus only, or okay, let me put it this way. Okay. So, a fast device through its you can also consider this I/O as the DMA controller, no harm. Okay, this is specifically shown here because this is a very general purpose I/O. This DMA controller is very much part of the interface now, as you can see. So, the device is going to put in its request to the controller will indicate to the CPU and the CPU will cut itself off from the bus and indicate to the controller. So, that DMA controller in place of CPU will sit and monitor the transfer from the device to the memory or memory to device depending on input or output. Okay. Now, when it does what it is, what is important is it is a block of data. Okay. Good. Now, when we deal with block of data, what is generally done? Say we have the memory, okay, we have the memory organized, right. So, we talk about some block of data, say this is the block, whatever be the number of bytes, some block. Okay. So, we can say that starting from this address, let us call this as start address, starting from this particular location for this length of block continuously data is going to be stored. agreed, because the data is going to come as a block, and also the DMA controller, as you can see, is having a very special role. It is only going to place the address of memory location and then generate the read or write signal appropriate, only that, right. This address, read or write depending on input or output, then once that is done, then next address, that address plus 1, then read or write, that address plus 1, read or write, like that it is going very fast. So, really it will take only about 1 or 2 clock cycles. Okay. For normal read or write cycle for CPU, it may take many clocks. The DMA controller will do it very fast, mainly because it is a hardware solution meant for this fast transfer. It has no other job to do, right. So, as part of the DMA controller, we have been talking about earlier, no, the hardware associated with the IO interface. Now, as you can see, because of this particular function, the hardware part of the DMA controller will have to include, that is the DMA controller, if this is the DMA controller, okay, the hardware part of it must include at least 2 registers. What is it? One which is going to indicate the start address, a register which is going to indicate the start address from where in the memory the data is going to be stored if it is input. Then the block size, generally that particular thing is called a word count register. How many words have to be transferred? So, that is called a word count register. So, you can see that in the interface a start address register and a word count register is needed. Good. And when will these be essentially stored? Start address and word count well before any DMA transfer can take place, is it not? Because it is not that the moment device indicates that it wants transfer, these things can be prepared. These things must have been prepared earlier, meaning well before the DMA transfer can start, even before the device can indicate that it wants a DMA transfer, okay, through this request. Okay. Well before that, these things must have been prepared. So, if you recall, I was earlier talking about 2 phases, one called chip configuration phase, right, chip configuration phase, and another one as the data transfer phase. So, when the actual data is transferred, right, DMA controller is going to take the place of CPU. Now, well before the DMA process can start, during the configuration phase, the CPU must have loaded into the DMA controller these 2 bits of information. What are they? The start address and the word count, which means a priori it must have been thought of. The device will request DMA transfer. When it requests, immediately as far as possible, we will see when exactly, we had talked about earlier, when the interrupt comes and when the interrupt is acknowledged. Similarly, here we have to discuss that when the DMA request comes and when the DMA request is acknowledged, we will talk about it. Now, as soon as CPU we say relinquishes the bus, that is releases the bus for what? For the DMA activity, right. As soon as that takes place, the DMA controller should know from which address and how much of data. Okay. So, these will be part of this. Now, in addition to this, you have the earlier things like status register and whatever we had talked about. Okay. Specifically for DMA, you need this. For status register will be there may be some other say a command register or whatever it is, okay. And then we talked about data buffer in general. Okay, good. Now, it is like this. Before the CPU proceeds with the program, it has got to configure all the IOs appropriately. Specifically in the case of the DMA thing, it must have loaded these 2 bits of information. When I say bits, I hope you understand right. These 2 pieces of information in the DMA controller, and then it proceeds with its own program, whatever it has. And when the device is ready, when a device which requests a DMA transfer, okay, when it is ready, it is going to indicate. Now, how does it do it? Generally, the signal that goes to DMA controller through from the device is called a DMA request. Well, as you got, okay, DMA request is a signal which is an input to the CPU. Finally, it will have to go to the CPU. Okay, the DMA request has to go to the CPU, and in response to that, the CPU will generate what is known as an acknowledged signal, that is a DMA acknowledged signal. In respect of some processors, this thing is called, for instance, hold. Why is it called hold? We will see. And this is called hold acknowledge. Hold is just you put someone on hold, waiting, no? And here you find CPU is put on hold. CPU will be waiting until this DMA transfer is completed. Agreed? That is why the name hold has come. Fine. The fast device, we can say fast device or also device which requires block transfer. Of course, that also needs to be fast. Okay. Then it puts in a request, and through the controller the request will go to the CPU. Finally, the CPU, it is an input to the CPU. Now, as before, the DMA request, as we saw in the other one, interrupt, the DMA request is also an asynchronous input, is it not? It is not synchronous. The device, when it is ready for transfer, when it is ready with the data, it is going to indicate. It is an asynchronous input. DMA is also an asynchronous input. And what did we say in the case of interrupt? In the case of interrupt, we said when an interrupt request comes, the CPU will complete its current instruction cycle, and that is going to cause some delay, right. Now, that is, we have an instruction cycle, right. We have an instruction cycle, and that consists of quite a few machine cycles, and that consists of few states. This is what we had indicated, right. Each one is a machine cycle, and here each one is a state. Okay. Remember, this is the very first thing we said. We said instruction cycle consists of, let us say, a fetch and an execute, and every time the CPU accesses the bus, there is a machine cycle. Now, the DMA request can come anytime during the instruction cycle, okay, which means during any machine cycle it will come, right. Let us suppose this particular thing has come, say, at this instant, that is, the DMA request has come at this instant, maybe during some state. Now, what is to be done? If this were an interrupt request, we know that at the end of the instruction cycle the service will be taken up. Now, if it were a DMA request, now that is halfway through the machine cycle it is coming. Now, what is a machine cycle? Machine cycle is essentially what is it? It consisting of CPU placing an address indicating a read or write or any other special control, and then finishing that part. Okay, that is what is in the machine cycle. So, and then what happens in the case of DMA, the CPU is not going to be used anymore. That means the register contents, whatever is there in the stack, everything is going to remain intact with the CPU. That is, the processor's state is not disturbed. Agreed? Processor state is not disturbed. So, unlike interrupt requests, in the case of a DMA request, the CPU can relinquish the bus at the end of the current machine cycle. Is it not? Why? Because at this point, that this is the end of the machine cycle. At this point, if the CPU relinquishes the bus for the controller, the CPU still holds all the information in its register. CPU is not involved in the DMA. So, at the end, when this thing DMA controller indicates that it has finished everything, then from the next machine cycle it can be started. That is not much of a problem, right. So, this way you can save some time, and sometimes it need not even be the end of machine cycle. Why? Because we have seen earlier that not in all the states we have bus activity. Not in all the states we have, that is, suppose in a given machine cycle, the last state corresponds to incrementing a register, let us say. It is a pure CPU activity, the bus is not involved, because one basic activity, that is what constitutes a state. Assuming in the last state in a given machine cycle corresponds to a incrementing of a register, it is not involved with the bus. So, we can even say that in response to DMA request, normally at the end of the machine cycle the bus will be released by the CPU. It need not really be strictly at the end of the machine cycle, because it can be 1 or 2 states earlier. The point is the bus should not be involved anymore in that particular cycle, machine cycle, that is what it means. Okay. So, that even when the bus is released to a DMA controller, if there is a CPU's internal activity, that can still go on, there is no problem, right, fine. So, this is one difference between the response to a DMA request and the response to a interrupt request. Okay. So, these are the essentially 3 modes of data transfer, and believe it or not, these are the only 3 modes of data transfer, there is no other way. The one in which the CPU is involved, the one in which the CPU is not involved in checking whether the device is ready, but CPU is involved in the data transfer. The third, in which the CPU is not at all involved, it is just kept aloof. So, we say the CPU is kept in suspended animation, we may say that, right. CPU is kept in suspended animation, and it is going to wait until the DMA controller releases, okay. That is, until the block of data transfer is over, the CPU will be kept in suspended animation, and at the end of the block transfer the controller will release the bus to the CPU. So, now you can see that CPU is usually the master, and in this case instead of this master another master takes its place. Okay. So, you can see that CPU is also a processor, DMA controller is also a processor, but then DMA controller is a special purpose processor meant only for data transfer, nothing else. Good. So, the third one in which the CPU is not at all involved. The first one CPU is fully involved, the second one CPU involved only in data transfer, the third one CPU is just said okay keep off, now you can't handle this okay, data transfer, then some other faster person will come and do it and the CPU is kept in suspense. Right. These are the three modes of data transfer. Now, we will go into the details of some of these. Let us look at some details about each of these modes of data transfer, essentially what the programming will look like. Okay. Now, if you take the programmed I/O, that is the very first one, essentially it would be first checking the status, no, and then doing the data transfer. Now, I think I will skip some of these things. Suppose you want to transfer say 5 bytes of data, okay, and assuming the device is byte oriented devices, that is generally we talk about like this, a device may be a character oriented or a block oriented device. Okay, there are two types of devices, say character oriented or block oriented. The block oriented device is what is the kind of device that we had come across already in the DMA. Now, in the case of character, a character is say A to Z, any numbers, special symbols. Generally, you just need only 1 byte, no, 1 byte for one character. So, these devices will be generating byte by byte, that is character by character it is going to generate. Okay, these are character oriented devices. A block oriented device is a block of data. Okay. Now, let us just assume that we are dealing with a character oriented device, which means essentially generates byte, and let us assume that in our situation the CPU is going to look for just 5 bytes of data, right. So, when 5 bytes of data is what is looked for, essentially the CPU is going to check whether the device is ready. If it is ready, then it is going to move 1 byte and then keep track of it. Okay. So, essentially a counter will be used, a counter will be set to 5, let us say, and after the transfer of every byte the counter contents will be decremented. So, that when the counter contents come to 0, we know that 5 bytes have been transferred. Now, those details I will just skip, I will not enter all those in the part of the program. Okay. So, let us say first what is programmed I/O, first you have to check the device whether it is ready. We know that the device being ready can be checked by looking into the status register, is it not, status register, and recall I also said the status register, for instance the very first bit of whatever be the size, let us assume a byte, this thing, whatever be that. So, let us say the MSB, that is the most significant bit. Now, this particular bit, depending on whether it is 0 or 1, it is going to indicate whether it is ready or not ready. Okay. That is BC. Now, let us assume 0 means if this particular bit MSB, most significant bit, if it is 0, then let us say it hardly matters how you do it. Let us say the moment the device is BC, okay, and if it is 1, the device is ready with the data. Okay. We need to know all this in our programming. Good. Let us we have to assume a few more things, right. That is, this particular register must have an address, is it not? The CPU generally addresses the status register and then reads the contents. So, we will just call that address very simply, okay, mnemonically as device status. Okay, device state is the address, just we are using a symbol, okay, instead of a specific address. And then there are many things that we can do. In I/O transfer, there is one method, I think I have not talked about it earlier, maybe I will explain that because it will be useful. In the I/O transfer, how exactly you split the I/O space? What do you mean by I/O space? That is, we have a total memory space given by the address. We have, say, an n-bit address. Okay, we will start with an n-bit address. Okay, and n-bit address is going to mean the total address space is going to be 2 to the power n. So, that is the size of the total address space. So, that is the total address space. Now, this entire total address space can be used as memory space, in which case you can have other, say, m bits or so for the I/O to indicate the I/O space. Okay? Or this total address space 2 to the power n, okay, suppose this is the 1 2 to the power n, that is the total address space. This can also be divided, say, into 2, exactly, let us say we are dividing into 2. That is, let us say this is the low address, this is the highest address. Then what is the address of the lowest location? That will be address 0. The address of the highest will be 2 to the power n minus 1, is it not? So, the total thing is 2 to the power n. Now, this n bit address, if you just see, okay, n bit address, you just take the most significant bit in this, okay, whatever be that size, the most significant bit. Now, this lowest half will be indicated by this MSB being 0, is it not? MSB being 0 will be indicated by this lowest half, because it is exactly half. Now, this MSB being 1 will indicate this top half, agreed? Okay. Follow? MSB when it is 0, we will be having n minus 1. So, 2 to the power n minus 1, that is exactly half. Okay, that is 2 to the power n minus 1, not this one. So, that will be the size. Okay, n bit address, you leave this, then you have n minus 1 bit address. So, 2 to the power n minus 1 will be 1 half. You just add one more bit, then you have another 2 to the power n minus 1. Now, suppose I allot this low space for memory and this high space, let us say for I/O. What does it mean? It means all the addresses, okay, all the addresses starting with MSB 0, most significant bit, if it is 0, it means it is a memory address, and all those addresses starting with MSB 1, that means it is an I/O address. Okay. Now, why do we do this arrangement? There are many reasons. One thing is we can use one instruction, right? Now see this, supposing I say move and let me follow a format. I will first give the format. Let us say move destination comma source. Okay, if this is the format of the instruction, move is the opcode and then we are referring to two locations, from where to where. Okay. Suppose I have an instruction move and destination, let me take it as a register, okay, some register in the CPU. I will just call it, okay, R for register. Okay. Now, n bit address, shall I assume just a 4 bit address for simplicity? So, 4 bit address I will assume, and I am going to give an address here. To indicate it is an address, I will just use the character A, okay, like I am using R for register. For address I am just using A. Now, then I am going to give just a 4 bit address, right. Suppose I give a number like this 0 1 0. What is this? In this 4 bit address, this is the MSB. MSB is 0. 0 means it is memory. Okay. So, the effect of this particular one will be to move from source to destination. Now, all this I am talking about mainly because I have to develop a program and I will use this format. Okay. Now, that is the reason I am just digressing and then explaining a few more. Instantly there is some concept also you will learn. It says you are moving and from this address, and where is where exactly physically it is? It is because the address starts with MSB 0, it is in memory. Okay. So, basically the effect of this is to move from memory, specifically address 010, because this is only indicating memory or IO, right, in this particular address, to register. So, this is going to cause a movement from memory to register. So, I will just put it as there is some movement from memory to register. Now, the same instruction I will use move, right. I will use the destination same register R. The address I am just making a small change. What is that? I am just making, instead of the MSB 0, I am making it 1. Now, what does this mean? We have said earlier, if MSB is 1, it refers to IO address. Now, what is the effect of this? It says move from an IO device of address 010 to register, from IO to register. Now, what has happened? Earlier we are moving data from memory to register. Now, in this, with this instruction we are moving from IO to register. What is this? This in fact is a memory read operation, whereas this is a device input operation. So, I have just what is it I am doing? I am using the same instruction. By using the same instruction, I am either dealing with memory or with IO, mainly because I have arranged in such a way that the total address space I am dividing in such a way that 0 is corresponding to memory, which means essentially all those addresses should correspond to memory block, and all the device addresses must correspond to IO devices. Okay. In hardwiring we have to take care of that. All right. Now, that is the hardware part, but as far as software part is concerned, what has happened? I am using the same instruction either for dealing with memory or with IO. In other words, when I say same instruction, we can say the same memory referencing instruction can be used either for memory or IO transfer, right. Otherwise what happens? If I use this entire address space for memory, then I need another set of address for IO, right, because you will be having the one address, let us say 0010, which will point to memory, and the same address 0010 which points to IO. Then how do I distinguish? The only way I can distinguish in that case is to have separate IO instruction. Okay, I would use separate IO instruction in case I use the entire address space for memory, whereas here I do not need a separate IO instruction. So, this particular scheme in which the address space is divided and IO space is mapped into the memory space, okay, this scheme permits me to use a memory referencing instruction itself either for memory referencing or for IO referencing. I do not have to change the instruction. Good. This scheme is called a memory mapped IO. Essentially it means the IO space has been mapped into the total address space, and there is a price I am paying for it, is it not? What is it? My memory size gets reduced. My memory size gets reduced, is it not? Agreed. But the advantage is I do not need a separate IO instruction. Now, both the schemes are there, it all depends on how you connect. Now, if we have a separate memory space and IO space, then I can have the whole 2 to the power n address space for memory and maybe another 2 to the power n, which generally you do not need for IO space. You do not need 2 to the power n, no, because we will talk about 16 megabytes for memory, but you are not going to have 16 mega devices, right, maybe just 16 devices itself may be too many, right. Good. So, in the other one, in case I use the total address space for memory and I have a separate IO space, that is another m bit instruction for m bit address for IO, then I have to use separate IO instruction. In that case, that is called an isolated IO, okay, isolated IO scheme, and sometimes it is also called IO mapped IO. Some people I think got the motivation from memory mapped. So, both are same, isolated IO, and that isolated IO is understandable, that is IO space is separate from memory space, it is isolated, and because this particular one is called memory mapped IO, so they also call this as IO mapped IO, alright. Now, I will use this particular memory map because it is easy to write the program. I would use this for generating a program. Now, quickly let us see 1 or 2 lines of the programmed IO. First, checking the device status. So, what I would do is say the first point is move, okay, let us say to accumulator. I am following the same format, move destination source. So, move to the accumulator whatever you have in the device status, okay. So, that is the address, that is just nothing but moving the status word to the accumulator which is in the CPU. And what did we say? If that particular word is positive. Why do I say positive? Because the most significant bit is 0 and that corresponds to the sign. Generally 0 is taken for positive and 1 for negative, is it not? So, I can just say next branch plus, meaning in case this device status happens to be a positive word plus, plus word, then wait, that is the label. That is, we say keep waiting, that is keep checking the status of the device, right. Next, that is the process is going to take this instruction and then this instruction, and now it can come to this instruction only if when only if it is not plus, meaning the device, when it is not plus it means it is negative, which means it is ready, the device is ready, the data must be available in the data buffer. So, now just see the here, what is it I am doing, device buffer, that is you can call it device buffer or data buffer, whatever it is, like status register, the data buffer. What is it I assumed? I assumed for input, is it not, because from the data buffer the data has been moved to the CPU accumulator, which is input. So, I have assumed actually an input device. So, these two for checking the status and seeing whether the device is ready. If the device is not ready, as per this program it is just going to loop here, it will keep waiting. So, this instruction will be taken up only if the incoming word is negative, and that will be negative if the device is ready. The device is indicates that it is ready when its buffer has the data. So, at this point when it comes, it means that the data buffer or the device data buffer is having the data which is input. Okay. So, previous to this you have say some initialization like at 5 bytes or 10 bytes or whatever, all those things, and subsequently whatever you want to do. So, this is essentially the crux of the this programmed IO technique. Okay. So, this is for checking the status, this is for effecting the data transfer. Now, you just see with one instruction I am doing IO, and the same instruction I can also use for memory referencing. Now, that is essentially because I am following a memory mapped IO. If you have isolated IO, slightly the program will alter. You will have to use in instruction or okay, because you are dealing with the in and out instruction depending on what the device is, if you are having a separate IO space.